Hello everyone. For this tutorial video, I would like to explain techniques used to compute limits directly instead of simply guessing their values, and convenient rules/shortcuts you can use to make your computations easier. The first rule is, if the function of x is a constant throughout the whole graph, then the function as x approaches a is still a constant. And this computation makes sense because a constant is still a constant. It will not change depending on the x value. Similarly, if we have function of x equals a as x approaches a, we can state the limit is exactly a, which if you looked at the graph of this type of function, you can see why this is true. As at any point on the graph, the function is well behaved enough that the limit can be stated as exactly equal to the function at that point. With these two most simplest types of graphs proven, we can prove limits of combinations of functions by simply combining these types of functions with each other. For example, the limit of a sum or difference is simply the sum or difference of the individual limits, and this can be proven with two different constants, so we will choose 2 and 4 for argument's sake. And we see the limit of function of x equals 6 is still 6, as with any constant, but it is also the limit of function of x equals 2 plus the limit of function of x equals 4, because of the way constant functions behave. Similarly, we can state that the limit of function of x equals 2 equals the limit of function of x equals 6 minus the limit of function of x equals 4. We can prove the limit of a product is simply the product of the individual limits by doing function of x equals 6 equals function of x equals 2 times function of x equals 3, and so the limits would have to multiply out. Similarly, we can see the limit of a quotient is a quotient of the individual limits by doing function of x equals 2 equals function of x equals 6 divided by function of x equals 3. But the catch is, with quotients, the denominator cannot equal 0 because you would get division by 0, like with normal arithmetic. Now that we have proven basic arithmetic tricks for limits, this allows us to prove a few more special properties, namely, that the limit of function of x raised to the power of n is simply the individual limits multiplied, and this is simply a special case of the more general multiplication rule, where the multiplication is a function of x by itself. If we know from algebra that the square root is something raised to the power of 1 over n, it follows that we can use the powers of function of x, what we just proved, to prove the nth root of a function. So the limit of a root is simply a root of the individual limit. Lastly, we can prove that we can factor a constant out of a limit, as it is simply a special case of multiplication of functions, where one of the functions is a constant. And the first thing we proved in this video was that the limit of a constant is exactly equal to the value of that constant. The very last tool we would like to prove is that the limit as x approaches a of x raised to the power of n equals a to the power of n. And this is simply a special case of the exponential proof, where we limit our function of x to be x. If you are curious, all of these are valid for the one-sided limits from either direction as well. But since we remember from the previous video that the normal limit existing guarantees the existence of both one-sided limits, I decided to prove the normal limits alone, so that way we do not have to manually do 2 extra proofs for each case. With all of our tools out of the way, we can evaluate some functions, such as the limit as x approaches 2 of 3x squared plus 5x minus 9, which would be the limit of 3x squared plus the limit of 5x minus the limit of 9. And we know all of these functions are well behaved enough that we can simply evaluate the function directly for the limit. So in conclusion, the limit is exactly equal to the function at the point specified, which evaluates to -7. Since we have seen in this example that all the individual terms of a polynomial are well behaved, a polynomial by itself is also well behaved. So the limit, as x approaches a value of a polynomial, is simply the function at that point. So now that we know polynomials are well behaved, we can evaluate rational functions or ratios of polynomials by doing the same trick as in this example. We break the ratio into the limit of the individual numerator and denominator, and then simply plug in the x point specified for the limit. However, because it is a ratio, aka a fraction, if we have 0 in the denominator, it would not work using the techniques we have. But in this case, we get 13/6, so our tricks are still valid. One final thing to note before we move on to the next video is that constant functions, linear functions, and polynomials are not the only functions that are well behaved. There are a couple of others we should take note of. In particular, from graphing it out, cosine and sine are well behaved for all x's within their domain. Secant and tangent are all well behaved, provided their denominator does not become 0, or, from their trig definitions, cosine of x equals 0. Similarly, cosecant and cotangent are all well behaved, provided that sine of x does not equal 0, as sine of x is in the denominator of these functions. An nth root is well behaved if the n is an odd number, and an nth root is well behaved only for x greater than or equal to 0 if the n is even, because of the fact even exponents only give positive numbers. An exponential function of the form base to the power of x is well behaved for every x value, and any logarithm is well behaved provided x is greater than 0. And because of what we proved at the beginning of the video, any arithmetic, sum, difference, product, or quotient of these functions must also be well behaved, provided in the quotient you do not get division by 0. So now that we have more functions in our toolbox, we can take more sophisticated limits such as this by simply evaluating the x at the limit point asked. We see that all of the functions are well behaved for any x value except for the natural logarithm ln, but in this case the ln is also well behaved because of the fact our x is greater than 0. So we simply plug and play and compute all of these values, and we get approximately 8.185 for our limit. Now that we have figured out basics of finding values of limits, we can explore more complex functions that are not as well behaved in the next video. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.